So here's a fact of mathematics that we're not going to prove, but any continuous function can be here, windows open, can be approximated with a polynomial on a finite interval. So, as I say, we're not going to prove this or even talk about it in depth, but I mean, you've probably seen the concept of linear regression and quadratic regression and these various polynomial regressions. And the reason that polynomials are such a natural tool for regression is this statement that assuming the quote unquote real graph is continuous, a polynomial will do to approximate it. And this isn't exactly what we're going to talk about today, but it's going to lead right in to what we want to talk about today. Let's see this statement in action with the function, the cosine of x. And let's look at some polynomials that are going to approximate this function around the origin, near the origin, I should say. And okay, doesn't quite know what to do with that. We'll see where this formula comes from sometime this week. It has a factorial in it, notice. I keep promising you that factorials show up in major applications. This is only a second degree polynomial, but near the origin, so around here, it's already doing a very good job of looking like the cosine. We increase the degree. Again, we'll see where this comes from, although you might already recognize the pattern. It's an alternating polynomial with the even terms, so the second, fourth, sixth power over the factorial, 2 factorial, 4 factorial, 6 factorial. And you see, I mean, this is doing sort of in this magnification, the cosine and this finite polynomial are doing a really good job of approximating one another. Or I guess it's a little weird to say the cosine is approximating the polynomial, but the other way around. And this is really significant. And its significance might not be immediately apparent, but the cosine is a really complicated function. I mean, like working with powers of cosine and doing trigonometry with powers of cosine. We have an entire chapter sort of dedicated to that, and it still doesn't work well if we have an even power. So I mean, the cosine, hard to work with, hard to do calculus with. A finite polynomial, easy to work with, easy to do calculus with. If we want to integrate this, if we want to differentiate it, we're just using the power rule. So obviously, this approximation only works on a finite interval, but a lot of the time the cosine is going to be in a finite interval. Like if the cosine is an acute angle, then we're only interested, come on, over. I cannot make the cosine overwrite the approximating function. But if x is an angle, which is sort of the classic application of trig, then the cosine might very well be stuck in here, and the cosine looks like this polynomial. In fact, we didn't need to go nearly so far. The cosine looks like this polynomial with only these three terms. And maybe we could just, if we have a power of the cosine, or the cosine is otherwise hard to work with, maybe we could just take this hard to work with function and replace it with this easy to work with function. And that's the idea behind, well, what we're talking about today, the idea behind power series. Power series, notice, so that sort of pose a question, a rhetorical question, because I'm going to, cannot make, I guess I'm going to like increase the thickness of this line so that we can still see it. So the cosine looks like this fourth degree polynomial, but only up to a point. I mean, obviously, if we're looking at this part of the graph, the cosine and the fourth degree polynomial no longer look like one another. But I've already observed this pattern. The more terms I add to this thing, you see it spreading out. From this, which really only looked like the cosine around here, to this, which looks like the cosine on a much bigger interval. And the more terms we add, the more this looks like the cosine. And of course, you know, on Desmos, I can only write finitely many terms, but we've seen the idea of taking an infinite number of things and adding an infinite number of things together. So the question we'll sort of be investigating is, if, no idea where that W comes from, if we consider infinite degree polynomials, see this word approximated, and something we've done an awful lot in calculus is take something that's only an approximation and try to make it exact. So if we look at these sort of infinite degree polynomials, if I could go back to Desmos and just keep that pattern going forever, will this approximation stop being an approximation and start being exact? Will continuous functions equal these infinite degree polynomials? Usually when I've asked a question like that, I've been sort of fishing for an affirmative answer. The answer here is a little complicated. Most of the time, yes. For a lot of very important functions, yes. For every function, no. But we don't really have the groundwork yet to ask this question. Let's get some definitions on the board. A power series is a series of the form, let me make C sub n x minus a to the power of n, and we start at 0. And we start at 0 because starting at 0 gives us a C sub n term that does not have x's attached to it. It gives us a constant term for this infinite degree polynomial. And the first and most important thing to recognize about a power series is that a power series is a function. It has our variable x in it. X can be any real number, potentially, although we'll talk about that. And different values of x will give you different results. In fact, different values of x can influence whether this converges or diverges. So for certain values of x, this might be a perfectly nice convergent series. For other values of x, it might diverge. So this is a power series, and a power series is a function. And that number A is called the center of the power series for reasons which will become obvious pretty quickly. And let's look at a quick example. Let's look at an example where we already have all of the tools we need to analyze it. Am I writing up there? Sum from 0 to infinity, x sub n. So I say that we already have all of the tools we need to analyze this thing. if X is a finite number, then this power series, and remember X is a variable, X is taking on values. So if X is 1/2, for example, Hypo City this morning, then what sort of series is this? So a harmonic series, the denominator changes like so. Good guess, though. This is a geometric series because to go from a term in the series to a next term in the series, we are multiplying by a constant. We're multiplying by 1/2. And this is a geometric series that starts at 1. And it has an R of 1/2. And this is a convergent geometric series. And the reason it converges is that the radius R is less than 1. If X were 2, this would still be a geometric series, but now it would diverge because 2 is greater than 1. So this converges and only if the absolute value of X is less than 1, and we know what it converges to. It converges to A divided by 1 minus R. Here, R is X. You know, when we let X be 2, R was 2. When we let X be 1/2, R is 1/2. A is the starting value. A is 1. So let's take a look at this. We cannot go to Desmos and ask it to graph an infinite degree of power series for us, but we could certainly go up to 5 or 10 or a relatively large number and see what happens. So here's 1 divided by 1 minus X. Let's see. We're looking at what happens between -1 and +1, or at least our claim is that this power series equals this function on this interval. I don't know if it's me or if these are genuinely kind of hard to see. Let's get some pick lines here. And let's look at 1 plus x. And I guess I'm now going to have to make all of these lines like this. 1 plus x, even though it's, only 2 terms, the constant term and the first degree term, this is approximating this function pretty good. It's approximating this function at around 0, around the origin. You may remember from calculus 1 that that functions look like they're tangent lines if you zoom in enough, and that's what's happening here. This is the tangent line at 0, and if we zoom in, it looks like the tangent line. We go up to x squared, and we already see difference, well, of course we see a difference. It's going from linear to quadratic. But what I mean is that we do not have to go very far before this function goes from looking like this curve on a tiny interval around the origin to looking like this curve on a large chunk of the graph. I think I mentioned 10. Let's make that our stopping point. So we do see that even when we go up to 10, I mean, there is this value here where things sort of are breaking down. We could make this look like the function here, but we need to keep doing this past the point of reason. And it's harder to see because it's shooting up. But we see that when we get close to this border as well, these lines are disentangling themselves, and you see, well, here's the curve and here's this approximating polynomial, and we can clearly see the difference between them. But around 0, this is doing a really good job of looking like this curve. And if I didn't have to stop somewhere, if I could just keep going forever, this would look more and more like the curve, even in these regions here. And in the infinite case, the polynomial, the infinite degree polynomial, would exactly equal this curve. So let me make an observation from this. I mean, this is an important observation in itself. What I have written here and what I have written here don't look exactly the same, but that's just because I'm not bothering to write every term in. This is a power series. It has the exact form of a power series. We normally don't bother writing in x minus 0 when the center is 0. but 0 is the center, and going back to this, here's, well, y equals 1, looks kind of like nothing, but here's 1 plus x. Here's the center, here's 0, and you see that this approximation is good on a little interval here around the center. And as we increase terms, the interval this approximation sort of looks good on is again an interval around the center. And that's just going to keep happening. Again, this is a good approximation in an interval around the center. And I mean, that's where the word center comes from. It's the center of the interval where this approximation is a good approximation. Outside of this interval, observation number 2, we can add as many terms as we want, and this will never be any good. Like, we're never going to make this function equal this curve here, or come close to this curve here. And we're not going to be able to make it come close to this curve here, no matter how many terms we add. And I mean, that's not really surprising because this power series doesn't converge over here. It's going to either positive or negative infinity. Of course, it can't look like this finite function. Sort of putting these observations together, we have a notion called the radius of convergence. So say that we're using a power series to define a function. Let's see. Well, this power series can converge or not, depending on what x is. We saw that with our preliminary example. It converges if x is less than 1 in absolute value, and it diverges otherwise. It turns out that convergence is always going to look something like that. It's impossible to have a power series that converges on the rational numbers and diverges on the irrational numbers, for example. It's impossible to have really complicated convergence. There are only 3 possibilities. It might converge at a single point. It will always converge at x equals a, because if we let x be a, x minus a is 0, so all our terms are 0. Or it might converge everywhere. or it might converge on an interval centered around the center. And those are the only three things that can happen. It's one of these three. And you see we have the phrase radius of convergence here, and you see I'm using the capital R here, capital R for radius. So when we talk about the radius of convergence, if it converges at a single point, we say the radius of convergence is 0. If it converges everywhere, we say the radius of convergence is infinite. If it converges on a finite interval, well, the radius of convergence is the radius of the interval. And something that we are very interested in doing is finding radii of convergence. Let me comment just briefly on this, this last option, option number 3. So notice that the way I've written it as a single case, and we've got an open interval. We're not including the endpoints. And that's not, properly speaking, true. We might sometimes have convergence at the endpoints. So this last case is really 4 cases where we include or do not include various permutations. Let's see, what am I missing? I think you can waste a lot of time worrying about the details at the end point. That must be a heretical opinion, considering the amount of time some textbooks on websites spend on this. But I say, okay, what are we using these power functions for? Well, we're using these power functions so that we can replace complicated functions with polynomials. I mean, that's essentially it, right? 1 over 1 minus x, complicated function, in the sense that if, for example, we wanted to differentiate it, we'd need the quotient rule. If we wanted to integrate it, we'd need to use the natural logarithm. I mean, when we just see it like this, it might not look complicated, but from a calculus point of view, it is. 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th. From a calculus point of view, a really simple function. To differentiate it, we use the power rule. To integrate it, again, the power rule. So if we're interested in what happens around 0, we can just say, okay, well, this complicated function that's hard to work with, just looks like this polynomial that's simple to work with, okay, we'll just do this replacement. And of course, we're going to get some error, but we're always going to get error. I mean, if we're, working with trig, we've got, infinite irrational numbers on this interval. There are these infinite non-repeating decimals we can't even write down. And then we've got 1 divided. I mean, it really doesn't make sense to worry about error in the way that some people would do, because as soon as you start writing numbers down, you're going to get error. So that's, I mean, there's huge swaths of mathematics about measuring error and stuff, but in general, the fact that we'll get a little error doesn't bother me. I mean, what does bother me is that I can only write down so many terms before this starts being ridiculous. I mean, I've written down 5 terms here. 5 terms is already a lot. 6 terms, actually, because of the 1. I got up to 10 terms last time before I got sick of it. And I wrote down 10 terms, and this polynomial still doesn't look like this function here, around -0.8. And if I could add enough terms so that it would look like this function at -0.8, but what's enough? I mean, is it 100? Is it 1,000? At some point, the sheer number of terms I have here counteracts whatever simplicity I'm hoping to get from the function. So, we see the closer we come to the edge of this interval, the worse the approximation becomes, and the more terms we need. And, suppose this does converge at the edge of the interval exactly. Suppose this is included in the interval of convergence. Well, what good does that do me if I need to have a Billion degree polynomial before the polynomial looks like the function? I mean, the reality is that in the applications of this, we're keeping like 4 or 5 terms on the outside. So it's a very theoretical question of whether, what happens at this value, because even if it does converge at this value, I'm definitely not keeping enough terms of the polynomial to witness that convergence. So because of that, none of this really matters in an applied setting. What matters is that we either have convergence essentially nowhere, we have convergence everywhere, or we have convergence on an interval. And what I thought was going to be a brief comment took 8 minutes and brought us to the end of the class. So tomorrow we'll find radii of convergence. Looking ahead a little, the test we use to do that is the ratio test, almost exclusively. So if you, you've had the homework by now. I hope you're feeling comfortable with it. but if not, maybe give it another look before Tuesday, and I will see you on Tuesday. I've been emailing tests back. If you haven't gotten yours yet, just be a little more patient.